Vaidman from Tel Aviv, who will tell us about effective non-Hermitian Hamiltonians of pre- and post-selected quantum systems. Is this your talk? Yeah.
Yes. Yeah.
Please.
I think Joshua bringing me here and also helping me to move the lecture to the time which fits my travel arrangements. Essentially, it was kind of an accident that I'm here because I saw the title, Quantum and Classical Physics with Non-Hermitian Operators. And about almost 20 years ago, Yakira Aronov and myself had two works in which was playing or getting these non-Hermitian Hamiltonians. So I thought that if there is a conference on non-Hermitian operators and non-Hermitian Hamiltonian was kind of the main probably things it's supposed to fit. This is one paper, and then it was another paper. So I thought I should come here. Then after I kind of put my way here, then I look on titles and read papers and realize that this is a conference about PT symmetric Hamiltonians, which is not necessarily what we are talking here, because this, I think, effective Hamiltonians which I get, they are not, I see no reason whatsoever why they should be PT symmetric. So they can be everything. They just they non-Hamiltonian, and they also not the effective Hamiltonian. So it's not contradict with the fact that maybe not the real Hamiltonians are all PT symmetric. This is effective Hamiltonians, and they are not PT symmetric. They are not Hermitian, and they are not PT symmetric. In fact, they are sitting well inside the formalism, which is a two-state vector formalism. And I believe it's a useful tool for everyone. So I thought it will be, even I understood that this is not exactly the topic. I thought it will be a good thing to come here and to try to bring this idea of two-state vector formalism. In these two papers, there are kind of development about this effective, non-effective, non-Hermitian Hamiltonian, but I decided that it's pretty old. I think it's still interesting, but I thought it will be more interesting that I will give more new things. So mainly, so in the talk, the plan is here. I will talk later about this, the setup, conditional evolution, and then I will say that really which also give us non-Hermitian Hamiltonian, but it's not what really I want to talk about. And then what I want to talk about evolution of pre- and post-selected system, which is not exactly clear what I have to put exactly explain what I mean by this, because it's not a standard, the most standard way to think about. It's based essentially on two-state vector formalism. And I think the big part of the talk I will explain what's two-state vector formalism. But in addition, I will talk about some highlights or paradoxes. If they're not paradoxes, they're not kind of attract me. So I will talk about some highlights related to two-state vector formalism. One of them, it's also experiment which I was involved recently. The spast of a quantum particle. It's also related to three-box paradox, which I think it's interesting, and I will mention it. And another thing, I was trying to bring Yakira Aronov here because I think his thinking is should resonate very much with ideas of this going to complex plane. I was hearing from him the last couple of years that he wants to make really classical mechanics in complex plane, saying that it will give us quantum mechanics. So I will describe in the end of the talk, hopefully I will be keep in time, his result, which I think the most close to it and interesting kind of he puts imaginary values and put something interesting. So this is a plan. So the simple evolution, unitary evolution. I have a wave packet, and the color tells me how thick the wave packet is. And if most of my works is a beam splitter and the interferometer, so this is what roughly I understand. And this is unitary, and we want to go beyond this. So if we put here a detector and we consider conditional evolution when this detector does not click. Until now it's unitary, but now it's not unitary. Maybe here my animation wasn't so good, so let's do it slowly. We had this wave function here. All amplitude was sitting, here. And the next stage, we have less amplitude because we have split it in two. Until now it's all unitary. And then it's still coming here, and when it's entering, it became thicker, because for all this part we need this amplitude of the one particle, and even thicker here because we didn't get it here. And this is clearly kind of non-unitary effect which happened here. Maybe the basic one, it's a standard collapse. If we have our particle sitting here and here in a superposition, and we put a detector which does not click, but it make things non-unitary. You see, let me put it back. Here it was a half wave. Here it was a half wave. Oops. Yeah, I'm not very effective with this pointer. Clearly, the collapse of the wave function is clearly something non-unitary. Maybe we can look on continuous, which is maybe more interesting evolution. We have a wave packet moving toward detector. So we see it became thicker. It's kind of a non-unitary evolution. And I think it's interesting mathematics, and maybe one can really work on it. For example, we can consider a cavity, and then a ground state in the cavity, wave function, and then we can consider a different cavity when on one side there is a detector, and we consider a situation where the detector does not click. It looks a little similar, but it's not. So really this is kind of this is not unitary evolution, and one can calculate and see what's going on inside. And this is maybe one thing which corresponds to the title, like effective non-Hermitian Hamiltonian. I think that if you want to describe evolution of this particle on condition that there is no click here, it's a non-Hermitian Hamiltonian, and maybe it's interesting. But it's not what I'm going to do here. I'm really, again, considering similar system. Particles start here, we have a beam splitter, it's going here, and then it's found here. Sometimes it was no click, but there is a click here. It was started from here and end up here, not like no click here. And I really want to talk about evolution of this particle, which is kind of unusual. It had evolution and then click. The standard quantum mechanics tell us it's simple. It was unitary evolution until this collapse. But I want to ask, what was the evolution of this particle? And maybe even what was the time evolution of this time particle before it's come here, on a condition that we know that it found here. Can we take into account this information that it was found here? It's not a standard way, because usually we don't take information from the future. But now I want to ask this question. And even maybe for simple, I don't want this big wave packet, maybe this small wave packet. I know it found here, and I want to ask how I will discuss it, its past. The wave function split here and then collapsed. But maybe this part doesn't sound maybe very relevant. If it's started here, end up here, why should we talk about this? Maybe we should not. Maybe this is a description. So what was the evolution? I want to come back and to look what happened with the particle, trying to take into account the idea that it was found in some other state. So maybe here, or probably not. So what time evolution? Why would I like to know the time evolution? Because I want to know how it interacts with other system. The meaning the operational meaning for all this exercise is that I say that particles started from here, end up from here. Photons interact very little, but even they interact somewhat. What they did on the way? Did they interact just here? Or maybe they did interact here because the wave function was here. This is probably more reasonable one. This is kind of a more complicated situation. Bigger interferometer, but it looks conceptually similar. You see, everything which comes in, it's tuned in such a way that although if it would go here, if it will block something, it will go here, it can come. But everything coming inside go out here. And if we start with a photon here and end up click here, then it looks like that it's supposed to be, this is probably not relevant. This is probably the evolution of this particle. And so I'll start describing the experiment. We really wanted to test, is this a true story? Is really the photon started from here, end up here, was inside this kind of interferometer and end up here. So I will start with a description of how we asked photon where it was. We asked the photon where it was started from here until here. Where was the pre and post selected photons? Only, and there were two students, and Shimshon Barad was the head of the laboratory where it was done. But I was really went down into this basement in Tel Aviv and helped to do the experiment. How we ask photons where they have been? They don't usually talk. So we have to first we have to give them information so we can ask them something. And the way to give them information was the following. You see, this is a simple interferometer, and it might be here. We want to ask if it was here or not. So I want to give the photon information here. How I do this? I wiggle this mirror. I wiggle it very, very slightly. So, because when you wiggle mirrors, interference may spoil out. I wiggle it so slightly, so we had visibility of 98.5%. And this wiggling was so tiny, we didn't see the spoiling of this interference on this visibility. Now, when I wiggle it, the beam go up and down, and here there is a not normal detector, but it was a quad cell, which we use only up and down part. And we measured the signal, the current up minus current down. You see, it's when it's go up and down, of course, there is a current up, current down, and the signal has a frequency of our wiggling. And we look on the signal, and we look for power spectrum, and we found this frequency. So in this way, we can say the photons coming here told us that they were here because they gave us this frequency of wiggling in this place. We added another wiggling here with another frequency, and we also got this. Unfortunately, we could know if every photon goes two ways or one way because it was about 10 to the 13 photons in our experiment. But it was clear that at least some of them, or maybe every one of them, were both here and here. I believe that every one of them both here and here. But anyway, clearly that the photons were here and here because we got this information and this information. These two frequencies appeared in our analyzer. So this is kind of the way to know where was the photon inside the interferometer. The amplitude was the same, and the signal was more or less the same. This is really actual, yeah. What?
So does it mean that they have equal probability of visiting both places?
If you can say, if I believe that they really was, every one of them was both here and here, but this I believe in many word interpretation. You don't have to. You may, from my point of view, every photon was both here and here, which come here. But clearly, we got signal. Clearly, it was here and here. It was similar wiggling and similar outcome and similar signal. So then this was reasonable. Because photons were on the path they could pass. Wheeler once kind of had this idea, and we said, yeah, he's right. We tested it. When we blocked this, it's natural. Also, this was wiggling. We didn't see this frequency. Or when we took this beam splitter out, and when we take this beam splitter out, these photons kind of go out. They don't come to my detector. So detectors which come here, photons which come here, are not supposed to know. They were not here. And this is what we saw. So the photons told us well what was inside, where were the photons. So this was all natural. And then we did this more complicated interferometer. It's more or less like I showed before, with a little more complication, because I really wanted to know where the photons were and where they were not. So I added some mirrors on the way. We could do it without this mirror. We can just put it in the end. But then I would have nothing to wiggle and to test. Now, when I wiggle this mirror, I see that the photons were here. I also arranged that 1/3 of intensity was here and 2/3 was here. So we saw these big signals, and FE and FF. This 2/3 of amplitude, or maybe 2/3 of the photons come here. So we got strong signal here, strong signal here, and we got all this. This was done when we worked hard to make our interferometer tuned in such a way that it was destructive interference outside and constructive interference inside. So essentially, we didn't lose any photons. Every photon started from here, ended up here. They took maybe different paths, so I believe they took all paths, but never. This was almost no leakage. Almost everything comes here, and we saw that, of course, we got information from all this A, B, C, E, and F. They were everywhere. Then we make one more experiment with the same system, with the same wiggling. Everything was the same. The only thing was that we changed tuning of this interferometer by kind of moving all this together out a little, such that instead of constructive interference here, we get constructive interference here. So this was okay. We did this. Now these photons, 2/3, are lost. Nothing here. So I didn't show what we got, because I still want that somebody will tell me what was the outcome of our experiment before I show it. Any suggestions? C. But if I ask, then probably not C. Otherwise, kind of, it will be not interesting. Probably it was not exactly just C, or not, or maybe not C. I don't know. If it's, or you say it's impossible. I don't know. It took me 2 months to realize that it might be otherwise. C is very natural. C comes, all this kind of disappear. If it's not C, any other ideas? So what we got, it was A, B, and C. A, B, and C. No E, no F. So it's kind of photons were on the path they could not pass, because they told us they were here, but they could not have been here, because the interference, again, maybe not, we have visibility maybe 1% out here, but these signals are equal, you see. A, B, and C, with our precision, were exactly the same signal. The same wiggling, the same signal. So maybe it was some small leakage, but it's hard to understand how we got this. And it's also very hard to understand how we can get A and B without F, because reaching here, we can only reach through F. No F. No F, no E. Okay, I will give a solution how I see it, how can one understand it naturally, this puzzle. later, because I believe what explains it, it's a two-state vector formalism, which this is kind of the main thing which I want to present here. And I will come back to this experiment and to show how I can understand these results. Two-state vector formalism. The standard quantum mechanics tell us when we make measurement, we prepare a state psi that evolve forward in time. Two-state vector formalism tell us that if we make another measurement and we find some other quantum state phi, we should propagate it backward in time and say that in between it has the same meaning as this one. If I want to discuss system between two measurements, both psi and phi play equal role. The complete description will be by psi and phi, the two-state vector. They are not scalar product. Both psi and phi needed to describe system in between two measurements. The idea that I'm trying to say is that this one and this one are really kind of the same. We are not used to it. We are used very much to this one and this one. We are not, but not to this one. I have some pictorial thing which I think helps, at least me, to see it. Usually, how when I have, we consider a situation which photon was emitted here and founded here. Two-slit experiment, we know the wave function. This is the forward evolving wave function. Now I want to tell that there is also a backward evolving wave function. And if I have these two slits, this backward evolving wave function should be also very similar. Something like this. It started from detection. Detection now is creation of this backward evolving wave function. And it should go the same Schelling aggregation with minus the time reversal, so it's go backward in time. It's supposed to work exactly the same. The complete description are two together. In every time I want to look now, I have this forward and backward. Here I have backward and forward, all together. Now, how I can feel forward we know. For example, how we know that there is this wave function. One way to make this experiment, have these two slits, have a detector which is moving, and now this is really the graph of intensity as a function of a position of my detector. I see this interference picture, two-slit interference picture of my wave function. I want to say that there is also a backward evolving wave function. I want to think that here there is this backward evolving wave function. It exhibits the same type of interference.
But the backward will depend where the detector is, no?
Yes, I have a click here. So how I do it? I have a detector here. I don't move it. I detect all this here, and now I move my source. When I move my source, I see the same interference picture. Of course, this is the intensity of this detector. But from my point of view, this is a click in this detector, and this gives me a picture of backward evolving wave function. I will do it the same here or on any other place. It will be the picture of the wave function. Instead of the forward, in this way, I see the picture of the backward evolving wave function. So I want to say that psi and phi enter equally to description of my system, in particular time in between. Aronov takes it, in fact, he worked before I started to work with him in it, and it was my PhD, working with two-state vector formalism. Aronov takes it even more seriously than I do. He playing with the idea that maybe now there is a wave function coming from the future. I'm more pragmatic. Only after time t2, I'm ready to discuss this two-state vector. It was a measurement t1, was a measurement t2. I want to talk about past, describe my system before two measurements, so later. Here I say, given this measurement and this measurement in between, the complete description is this two-state vector. I already have this measurement. I already have both measurements. So what can I say given this psi phi? I say the complete description is not just psi and phi. What can we say? One thing is really if I make any strong measurement, von Neumann measurement in between, I can know the probability of outcome of any measurement given pre and post selection, and this was done by Aronov, Bergman, and Leibovich in '64. This is maybe a slight generalization of this formula. But then this strong measurement, I think it's also make all kind of interesting puzzles, and this formula brings some interesting things. But I think kind of more, at least maybe I was involved, it's about weak measurement. I say that's interesting part that if we'll make weak measurement here, weak measurement in such a measurement which will not disturb significantly psi and not disturb significantly phi. Then I claim that effectively we will measure weak value. This weak value, this is the expression for weak value. It might be interesting, it might be very big. If psi and phi are almost orthogonal, it might be very big. And it is complex. It's not a real number anymore. The weak value of Hermitian, observable, whatever, is a complex variable. It has kind of classical property A plus B weak is A weak plus B weak, which immediately can be seen. But it's not trivial about product. A B weak, not necessarily A weak B weak. Usually it's not. For example, if I prepare a spin up x, and then later I found spin up y, and I measure a spin in 45 degrees, the weak value, if I plug this formula inside, this is a definition of this spin in this 45 direction. I can easily see that sigma x is really 1 because I started with 1. Sigma y is 1 because I found 1. So it's 2 over square root of 2. So I get square root of 2. It's supposed to be only 1 minus 1. But in this case, it's square root of 2 outside of the range of the eigenvalues, because my scalar product is not 1. I want to make general statement that if I look in small time, that interaction of my pre and post selected system, it was pre-selected in psi, post-selected in phi shortly after. Any interaction to any observer, if I have kind of a Hamiltonian of this type, if I look for very short time, effectively I will interact not to C but to C weak. I can replace in this Hamiltonian at C by C number. This C number. But this C number is really might be complex number. Since it's a basic claim, let me even give a proof because it's just one line. I start with my system. Psi, this is psi of my system. Chi is my state of my measuring device. Then this is a coupling. This is a coupling for a short time, dt, infinitesimal time. Then I make post selection on phi. Now I can play with it. I just can, since dt is infinitesimally small, I can expand the exponent and to write it in this way. Now psi phi scalar product I can take out, and then inside I get 1 minus ig, and you see the weak value. Now again, dt is very small, so I put it back to exponent, and then I get something like this. I renormalize it, and I will get by measuring my external system, whatever it is, measuring device or everything else, couples to my pre and post selected system according to this unitary evolution, which is corresponds to this Hamiltonian. So Hamiltonian starting from h kind of general interaction, Hermitian Hamiltonian, come to this one, which in general not Hermitian. Now, this is for infinitesimal time. The work which we had, this work which I mentioned in the beginning, was the following. Consider coupling of many spins to one external spin. Now, all these external spins are pre and post selected in this state. This is really kind of a rare quantum event because I want all of them. I have many of them, and every one of them was pre-selected in up X. This is no problem. I can pre-select all of them, prepare them all up X, and then I post-select them in up Y. Probability for this is half to the power n, but theoretically it can be done for any n. Now I have a coupling G over n. So the coupling, when n is very large, the coupling is small coupling of each spin on the left side to environment, which is my external spin, is very small. If it's very small, so it will not be, I can consider this weak regime. So I can replace the coupling of every one of the spin by its weak value. If I have this coupling of scalar product C dot sigma dot sigma, let's look what I can say about weak values. Sigma x, the intersect one, I started here from intersect one, sigma z1 is minus I. It's easy to calculate that weak value of, if you start with up x and with up y, the weak value of sigma z is minus I. Of course, if you start with sigma x, the weak value of sigma x should be 1, and sigma y also 1. So this one and this one, and so now in all this Hamiltonian I can replace it by weak values, and I will get this Hamiltonian, and this is definitely effective Hamiltonian, which is non-Hermitian. And it has all kinds of different interesting properties. You're welcome to look more carefully and to ask me maybe later. I want to come back to a two-state vector formalism resolution of my experiment which I presented before. Okay. So we had this strange phenomena that we get. You remember, this photon was not supposed to come here. They were all kind of all left, but only for these photons came here. But we got information about A and B. So in some sense, I want to say that my photon, every photon which started here and ended up here, was also A, B, and C, or at least some of them. Although it looks like none of them, because all photons which enters this interferometer were lost. So, what is the two-state vector formalism explanation? Let's start with a simple experiment. Simple interferometer. See, even not interferometer, we have just beam splitter, and here we don't have anything, and we get a click here. This is a forward evolving wave function. But we found a photon here, so there is also a backward evolving wave function. It goes like this. And now we can look on two of them together. We can see that here there is no backward. Only here there is backward, also there is a forward. Only in B there is forward and backward. So if I take the simple property, the particle was where it was forward and backward wave function was present. Because the idea, we have to take seriously backward evolving wave function, as serious as a forward one. So we have to take both of them into account. Only here were two together on all these paths. So this explains that there is this click, there is this frequency and no this frequency, because my photons were not there. Let's go to this one. The forward evolving wave function. You remember, it was tuned in such a way that nothing goes here. Now the backward evolving wave function. you see, since it was tuned in such a way that everything coming from here go here, then everything coming from here should go here, and there is a time reversal, so everything which starts from here should go here. It cannot go here because of my tuning of my interferometer. So now we can look on the picture together, and then we see that on this path there are two wave functions. Here there is only one, and here there is only one. But inside inner interferometer also there are two wave functions. So my photon was here, here, and here. So it's not strange that we got this, because my photons were in three places. Photons was where forward and backward wave function is present. We look on the weak. We can look quantitatively. Weak value, you see. For weak value, we need presence of both of them. And in A, we have two of them, and it's not 0. In B, it's not 0. In C, it's not 0. In E and F, it's 0. When we make projection on E and F, because there is only one, another one, it's not here, so we got 0. So we get this picture. Weak values are important because the coupling, if we look on interferometer, we cannot make strong measurements. We only look weakly. So for every weak coupling, this is what's relevant.
So what you're saying basically is that you need PT symmetry to understand this, because you have to run it backward in time and then reverse the gain and the detector and the thing that's producing the signal.
I need T symmetry. P was not there.
But P means interchanging the detector and the source.
Yeah. You're counting the detector as the source.
But using this idea, I can get effective Hamiltonian, which is not PT symmetric. If I multiply Hamiltonian, I think even the Hamiltonian which I wrote, sigma x minus I sigma z is probably not PT symmetric. And I can make I can multiply by I. I can make, if I just take Hermitian Hamiltonian, multiply by I can arrange it. Will it be or any complex number? It will not be PT symmetric. So I don't. But what?
Have you calculated the eigenvalues of sigma x plus sigma y minus I sigma z?
I didn't, but I will be surprised if it's.
It's not necessarily. You're right.
Yeah.
And the reason is because your experiment has got enough. But you can make it PT symmetric.
Okay, but let me. I have 20 minutes. I want to also say the Akir's idea. So let me go. Okay. I can put it a little more quantitatively. I look on. This is a wave function which comes to this moment. The wave. In this moment, it's really in A, B, and C. Now, in fact, I can arrange phases, so it's just A plus B plus C. A is being here, here, and here. Something which go backward, it's also on this form, but it will be with minus sign in one of them. It should be, otherwise this interference, it tells me that it should be minus sign on one of them. So this is my two-state vector, psi and phi, A plus B plus C, A minus B plus C. This is a two-state vector of what's once called three-box paradox, which I will mention soon. And it has property that weak value in A is 1, weak value in C is 1, and weak value in B is minus 1. And in fact, there was an experiment measuring this weak value pretty long time ago. And my experiment is really similar, in which also, this is kind of looking on these projections, somehow I don't have this minus sign. Somebody will tell me why? Steinberg saw the minus 1. He made weak measurement of presence of photons A, B, and C, and he got that in B it was minus 1. I don't have minus 1. Yes, it's a power spectrum. I don't see the sign. So this is why I don't see the power spectrum. Okay, the three-box paradox is just this simple. I prepare a particle in A plus B plus C, and then I found in A plus B minus, here it's minus C, yeah, B when interchange, and I ask if the particle is in A. It was prepared in 3 boxes, found in 3 boxes. In between, I ask if it was in A. And is it in A? And in fact, it is in A always. If I look, I always will find it in A. Why? If I don't find it, it's collapsed to B plus C, orthogonal to this, and then it's impossible. So given my pre-selection and post-selection, it is impossible that I will not find it at A. But there is a symmetry between A and B, so it's always in B. And this is kind of strange. There is a single particle which, although pre and post selected, which I'm certain that will be here and here. Related to this in 2, I think, useful theorems, if you'll go to this business of two-state vector formalism, is say following. If I have a situation, pre and post selected, in fact, in which I'm sure that measurement of some observable C will give me some eigenvalue sig with certainty, then I know that the weak value will be equal to this eigenvalue. And if my variables are dichotomic, have only 2 variables, the opposite is also correct. If somehow I turn out that the weak value is equal to eigenvalue, one of the 2, then my strong measurement should give us with certainty. My 3 box is this kind of situation. We have this dichotomic variable, yes or no, present or not, projection operator. And we know with certainty it's an A. Therefore, the weak value in A is should be 1. We are certain it's in B. The weak value in B should be 1. Now, we are certain that it was only 1 particle in all these things. So, projection on A, B, and C with certainty is 1. So, the weak value of PA plus PB plus PC is also equal 1. But weak value are additive. So, from here we know that weak value of C is minus 1. So, in this way we can immediately see this minus 1. It was obtained by Steinberg in this experiment. Okay. Let me go to Yakir's story, which I think sounds very, although I think I kind of have resolution for me, it's look kind of a paradox. Yakir's story tells us that we can have 2 particles, 2 spin-half particles, which are separable. I mean, one is prepared sigma x up and found sigma y up. Another one independently prepared sigma x up, found sigma y up. Looks like one is in Tel Aviv, another one in New York. No connection between them. No entanglement, nothing whatsoever. But now he says that there is some correlations between them. It's not supposed to be. How we define correlation? He says this is really definition of correlation. Expectation value of AB minus expectation value of A times expectation value of B. Since they are separable, they are not supposed to get this is supposed to be 0. But again, look on a sigma z, spin in z direction here. Correlation between sigma az and sigma bz, we can view it as expectation value of the product minus product of expectation values. Now, let's calculate this. This is simple. Expectation value sigma az. We start with Abix, probability for z up, z down is the same, and this doesn't change it. There is no any preference. After we found again the post selection on y. So every one of these, in both cases, they're identical. So these are all 0. Now we need this is more tricky. What's expectation value of sigma a z sigma bz of this operator? Usually this is not true. Usually a times b weak is not a weak times b weak. But if they are separable, then it's very simple. Just plug in a formula for weak value, and we see that since we have different Hilbert spaces, very easy to prove that this is correct for this case. Not in general, but for this case. Now, we already calculated for this case what sigma AZ weak is. It was minus I. Of course, the same, minus I. So here we have minus I times minus I, which is minus 1. Sigma AZ, sigma BZ, this operator can be 1 or minus 1. It's dichotomic one. And it's minus 1, the weak value equal minus 1. We can use our theorem that if the weak value equal eigenvalue, then we know that this eigenvalue will be with certainty. So we are certain that in a measurement of sigma AZ, sigma BZ, we will get minus 1. And we get this kind of very strange situation. Two particles, they completely uncorrelated. Pre-selected, post-selected, pre-selected, post-selected. Now, we make measurement of sigma z times sigma z. And we see that they are correlated. They are always minus 1. This is correlation. This correlation get minus 1. Now, looking on this, it's very, very paradoxical. But I think the problem is with the definition. When we talk, from my point of view, when we want to talk about correlations, it's we have the system here. We need some outcome here, and then we look on the coincidence. Sigma AZ, sigma BZ is not this. This is an operator which we have to measure. It's a non-local variable. This non-local variable, we get this correlation minus 1. However, this is non-local variable. If we measure this non-local variable, we cannot measure it by measuring sigma z here and sigma z here. We have to make some very special arrangement, bring them together, or some correlated non-entangled particles coupled to them. It's some different story to measure this. It's different from kind of measuring something here and measuring here. So that because of this correlation measurement, we have this strange thing, which is you look on it, you get correlation between two uncorrelated particles. Sounds very strange. Maybe just to see why one can see that maybe it's not so problematic. If I take this system and change it by make it entangled. Again, let's say here I found that sigma x equal 1, sigma y equal 1, but I start with singlet, entangled pair. Here I also will find something very interesting between these two particles here. There is a failure of the product rule. Without post-selection, we always have this product rule. If A equal A and B equal B, then AB equal AB. Not for pre and post-selection. You see, if I ask what is the value of spin 1 for A, it means that what I will find if the only thing I measure is spin y for this particle. Since this is a singlet and I found y up here, this y up should be down. So sigma AY is minus 1. If I measure instead x here, since up x here, I get sigma bx minus 1. Again, if I make a non-local measurement of the product, sigma AY times sigma bx, I will also get minus 1. Minus 1, minus 1, minus 1. A equal A, B equal B, but it's not true that AB equal AB. Once Hardy made out of this, had some paradox which concluded that we cannot have a relativistic quantum theory, but I think all what he didn't take into account that when we have pre and post selected system, then we don't have the product rule. Okay, so my conclusions are that the pre and post selected quantum system are described best by two-state vector and weak values of all physical observables, and evolution of system coupled to pre- and post-selected quantum system is described by non-Hermitian Hamiltonians. Thank you.
Well, I
Yeah.
give myself the right to ask. Let's say you want to repeat this experiment, not with spins and time reversed symmetric Hamiltonians, but you want to do some beta disintegration, weak interaction type of experiment with break T. So in the post selection, you will have to modify what's going out of the detector in some proper way, in some well-defined way, in order to extend your idea to. I mean, there are Hamiltonians which break T symmetry, like quick interactions.
Again, I'm not a specialist, but I really believe that everything is completely unitary with time reversal. Like I know that when I put electron and look on the trajectory, I put it in change the velocity, it doesn't go in the same trajectory. Why? Because we didn't change the magnetic field. The T breaking of T, I have to change the appropriate magnetic field. I believe that everything is time symmetric. You just have to replace enough things to make. I believe that everything is unitary and time symmetric. I'm sorry, I'm not. I don't have this vision. I believe that quantum mechanics, as is, correct. Period. Completely. I want to hope. I want to believe that I understand nature. And so the only candidate today is quantum mechanics as is. And so from this point of view, I'm very pragmatic. I believe quantum mechanics is correct.
I believe in quantum mechanics too, but
Yeah.
weak interactions do break time.
Because there is something.
Nothing to do with magnetic field. It's just the Hamiltonian has explicit time breaking.
We need like there is no. It's similar to the fact that the electron in magnetic field break time symmetry, but it doesn't make that the time symmetry is broken in the universe.
No, there is difference because you are asking about electron QED. QED, of course, time reversal is not broken. If you put external magnetic field, it's not considered as time breaking. But in weak interaction, fundamentally, you break time reversal.
I don't know what one have to change fundamentally so it make it time symmetric. I'm not a specialist. I want to believe that there is something like this.
You need another universe.
What you're referring to with the magnetic field is time reversal is broken in the Lagrangian. The issue is whether time reversal is broken in the vacuum. In other words, the Hamiltonian can be perfectly time symmetric, but the vacuum doesn't have to be. That's what we think happens in weak interactions.
Okay, I better not comment on things which I don't understand enough. Yeah.
Just a second, there is order. I'll order it because I have to be just. Okay, please.
In some sense, you use the concept of measurement in two meanings. I mean, normally one expects that you prepare the system at time t0 and then you evolve to time t1. You see what happens. If you decide to also prescribe the result of measurement, so you move backwards and you say that you have non-Hermitian Hamiltonian. So my question is, could you reconstruct this non-Hermitian Hamiltonian which represents evolution forward in H and evolution backwards in H cross? Which means those two Schrödinger equations could meet in the middle.
This was.
If you prescribe complete set of pre and post selected states, you should reconstruct your non-Hermitian Hamiltonian.
First, when we have this system, we have many spins coupled to one spin, and this many spins was all pre-selected in one state and post-selected in another state. It's a very rare situation. After we did this, and then we look on this coupling, then this one spin fills this non-Hermitian Hamiltonian from the beginning till the end, given this. Now it was constructed exactly, the second paper was protective measurement of two-state vector. This non-Hermitian Hamiltonian had different eigenvalues for forward and for backward evolving wave function. So I can have two-state vector of my other spin, and it was kind of protected. So I could even look gently on this other particle. It was two eigenvalues, one set of eigenvalues like sigma x, and another value was sigma y from the future. So this was exactly how why it was constructed.
Can you go back to the interferometer?
Which one of them?
Probably this one, yeah. What?
So just to add on to Carl's remark, so here you have an open system because you have a leakage, those two channels going down. And however, you can make it PT symmetric. Now you can insert two gaining channels coming in from the left. And I presume if you did that, then you restore the amplitudes on E and F. And
From where you want that I will get?
Maybe you should come and point it.
well, I have to think rather carefully because I have to order it in time order in manner. But I presume it's from the left into the first interferometer. And
In which?
Yeah, first half.
Entering something here will not help me significantly.
You know what I'm saying is you
What?
can make it PT symmetric. So this picture can be enhanced if you have a loss here, a loss channel, and you can realize PT by balancing gain and loss. And here all you have is loss. So you can additionally insert two gains, one from the left of the first circular mirror and one from the left for the second mirror. And that would presumably restore the amplitude for E and F. And what might be interesting from experimental point of view in PT is to adjust the amount of gain and loss, because then one might see a phase transition. So that's, but I don't know if that's the case.
But you may even be able to do, the original upfixes also had loss without gain. And that system was just a similarity transformation away from a system which was exactly
Yes,
symmetric.
you move
And
everything back.
you move everything back. So it may already be possible to see, even in his system, a PT transition. But you'd have to do a transformation in both your pre-selected and your post-selected state. So I'm not sure if I know how to do that.
I never tried to, as a PT is new. The first time I had when I started to look in papers of you and others who coming here. So I never played with this thing with PT. You are welcome.
Just a second.
Well, because you have lots of
Guys, please don't diverge. Please, Boris.
Yeah, actually, I would like to ask maybe somewhat related, but much simpler question. Concerning the real experiment, if the experiment is run in the lossy medium, when you explicitly have some losses on the route between the source and the detector, and also on the inverse route, so by losses, effectively, also it's possible to consider gain, not only losses. But if you have losses, you will somehow explicitly break the time reversibility. Will this affect your observation finally?
What I see from this story, there is a simple principle. To see the effect of particles, I need two state vectors. If whatever I put here, losses, whatever, it's still no wave here. And if I put from loss, there are all kind of losses and no wave, backward wave here. I will see the same story. I will see a trace here and here. I will see these frequencies and I will not see this frequency. This formalism tells me immediately, I need two both. I don't know if it's they probably.
But I thought in the appendix to your paper, you show that you don't
What?
need. In the appendix to the
If you, I have this. If you want, I can look on. Yes, this is really the after the talk slides. That if somebody really wants, because this is kind of a completely crazy idea that I get here information about this. It should be explainable in a normal form, a single wave function, and this is explanation. If I look on the single wave function, because of wiggling, of course, I destroy a little this interferometer, and there is a tiny leakage here. This leakage was not seen if I would try to see my detector here, I will see nothing. However, there is a big wave from here, and it's interfere here. In the end, I get the same effect because this leakage is really kind of very wide. There is a tiny leakage because of this when I change and this interference of this leakage gives me this effect. Can be explained with single wave function. I believe quantum mechanics is correct, and you can work with single wave function and understand everything. It's much more complicated. You have to understand some interference, and sometimes very complicated interference. I can say immediately, if I want to talk about photons, where the photons was, I need to say these two-state vectors, photon was here and here and here. I can say, oh, there is this big wave function going all over, there is tiny leakage and interference, and I also can explain effect.
But the question was much simpler, actually. So I guess in your picture, you have roughly equal heights of the peaks corresponding to A, B, and C. If you run the experiment in the really lossy medium, will you still have equal heights, or they will become different?
If the losses on this area similar to this area, they will be equal.
And then we go to.
Okay, so for me, this experiment, two-state vector formalism, this experiment is very interesting because I always talk about the time reversal symmetry between the initial condition problem and the terminal condition problem. You actually the backward path is actually the terminal condition problem. So I think this is a way you can detect you can analyze the terminal condition problem. But my question is, but then in a weak measurement, if this is a really weak measurement, I think it's rather crucial to measure the phase or the sign of the weak values. Do you think it's experimentally possible to detect somehow detect the sign or the phase of the weak values?
Okay, first this -1 that was measured by Steinberg, and we also saw it in laboratory, but it was this wasn't the point we wanted to show. One may be kind of, since you said about the time symmetry, it was a little cheating. You see, this red one, I had a laser. The laser put this light like this. Here was a detector, and I put this green stuff as if I had a laser here putting back. What I had is a detector. If I want to be really careful, what's come out, it's not this green, but something very white, because everything, if the photon can come from here, it also can, my detection, it's time reversal. So if my detector get photons from here, so when I get click, it sends backward evolving wave function all over from where it could get a click. So the picture, so there is no really time, it's not exactly time symmetric picture. This one is very far away. However, in the end of the day, all these are not relevant because they not come here. So they're relevant only in this part. But there is no time symmetry here between my source and my detector. Maybe I can construct particular with lenses and a special detector which detects only light from here, then it will be similar. As I described it, it was small cheating.
Two-step question. One, can you design cases where the denominator vanishes? And if you can, then is this the right quantity?
We essentially, the first paper was 87 about weak values, and then Sudarshan puts a paper about kind of what's the meaning of weak values, and he considered a situation of psi and phi orthogonal. And there are a little more papers in which people consider psi and phi orthogonal. For me, it's kind of a dirty stuff. We get, when it's not orthogonal, we get this value and it's well defined. When it's orthogonal, you can analyze it. There are interesting situations. Your measuring device has 2 bumps. There is nothing in 0, but there are 2 bumps but I find it not, I like some things which are simple and robust. You put this orthogonal, this explodes, and it doesn't have much meaning. But there are papers dealing with this case. This.
Some more questions? Okay, very brief one. Okay.
You said you had 10 to the 13 photons. What would happen if you have a single photon source?
Yeah, Alan Aspect is supposed to be kind of a guru of this thing, and when he had my talk about this issue, he said, oh, it will not work. I talked to him many times. I don't understand any. From my point of view, if you succeed to do it with tennis balls, it should work the same. There is now, I mean, it's supposed to work, and I was very surprised him to hear this question, because 30 years ago with Grandier, they made a Mach-Zehnder interferometer with single photons, and it worked. And it's the same story. So the only difference will be that my students, although he still didn't finish, wrote his dissertation, now he would even not start his experiment. He will not finish his experiment, because to make a single photon experiment with 10 to the 13 photons, we will need probably another 10 years.
I'm not sure if I've understood this, but if I think of the detector as a photoelectric detector, so a photon hits the detector and an electron is emitted. Now, if there's a wave sent back somehow, it's going to carry some energy and momentum. So will the electron that's emitted in the photoelectric detector have a different energy and momentum than we think? I mean, and the question is, does psi carry energy and momentum?
Phi?
Psi.
Yeah, psi is a forward one. Yeah.
Okay, well, phi. Does it carry energy and momentum?
What it's again the description. I don't. We need psi and phi together, and it's like if somebody there is this. I learned it from Aronov. He always has this Gedanken experiment with a universe in which arrow of time is going backward in time. So for him, it's if just if there's other memory arrow of time is different from this guy, this will be emission of a photon, although it will be a photon like this. But it will be exactly the same story, the same energy, all quantities was the same, just backward in time. You see, we can arrange the time. Standard quantum mechanics is time symmetric. So it's just boundary condition, Big Bang and whatever. We could imagine that maybe there is a parallel universe, isolated, in which time goes backward, and this will be exactly this wave function.
So what energy does the electron carry? The electron that was kicked out in the photoelectric detector?
In this, if we go backward in time, it was kind of kicked and then it came back, so the detector will be intact now. If you look backward in time and you go this way, at this moment the detector is, from this arrow of time, is undisturbed. It's kind of again in a ready state. This is how, so it will not have any energy. It had, so it's just time reversal picture. You have to time reverse everything. It's the detector stopped to know that it detected anything, and it's pushed the photon out.
If there are no other questions,
Thank you.